In this third video, we'll look to see how data compares to other data sets, and we'll see if we can deduce any correlations between those items. For this demonstration, I've chosen the height in inches and the height in centimeters to compare. So the first thing I'll do is I'll select both data sets, go to Insert, select the chart type of scatter plot, and you can see now that that'll assemble that information for us. One thing you may notice is that our data is scrunched up in the upper right-hand corner of this graph, and it's hard to see any meaningful differences because the scales are actually quite wide on both the x and y axis. Since we don't have students that are in the 0 to 50 inch range or 0 to 140 centimeter range, we can potentially delete that area from our graph in order to get a better picture of how the data looks. And so one way to do that would be to left click on the axes, then right click, and then select Format Axes. For our x-axis, which is inches, we can select 60. So 60 to 80 looks good there. If you look at this graph from far enough away now, all of this data might appear to be horizontal, which we know isn't true. The students have a range of centimeter height. So we can also adjust this axis as well. Let's set our minimum at. And now you can see that our data is distributed from the bottom left corner of the graph all the way to the top right column. Sorry, the top right corner. So next we can go through and we can add elements like axes titles. To speed up the process, I'm just going to hit Layout 1 in this case. Because we only have one data series plotted, I'm going to go ahead and delete this label or key. And now I'm just going to take a moment to fill in these appropriately. Remember, we have centimeters across the y-axis. And inches across the x-axis. Once again, these are kind of hard to read, so I'm going to adjust the color and size. And then I can do the same thing with the axis labels by clicking on the axis, changing those to black, and maybe making them a touch larger as well. So one thing that doesn't appear to need adjusted on this graph that we may want to do in future graphs is change how these things are separated. So you can see now they're counting by 2, 60, 62, 64, 66, etc. If we left click on the axes and right click, it'll pull up this Format Axis table on the right. And right now you can see that the major units are set at 2. If we wanted to, we could change that to 1. And now you can see it's counting in integral units from 60 up through 79. We could do the same thing over here. If we didn't want to see the data is dense in 5 units, we could change it to 10 to make it a little bit more sparse, but I think 5 looked appropriate to start, so I'm going to leave it at 5. Another thing we can add is tick marks. So in the Format Axis option, if we go to tick marks, you can see it says major type none. If I change this to outside, you can see that now it is putting small tick marks on the outside of the graph. This will become more obvious when we look at the x-axis since it doesn't have these horizontal lines in the background. So I'll select the x-axis, go down to tick marks, and for major type, select outside. And you can see now that these lines are aligned with the values below them. So, like we did last time, I'm also going to adjust. Sorry, that was the wrong one. Go down to line, change the line to black. And make it thicker to have it stand out more. So if we think about all the things that a graph needs to tell a story, it needs a chart title, it needs axis titles, in this case we have 2 axes. You need labels across the axis and units where appropriate. We have all of those things, and we have our data set graphed. Before I showed you how to change the color of our histogram, now I'll show you how to change those same features within a scatter plot. So likewise, you left click to select the data, right click to format data series. You'll see the window pop open over here. If you click on the paintbrush, the paint bucket, you can select marker. And under marker options, you can change it to built-in, which will now give you the option to select squares instead of circles, etc. Let's go back to the data series, marker. So we have squares, we can make them larger. Let's increase those to size 8. We can go to solid fill and we can change that to maroon. And then we can do the same thing. So if you look closely, you can see our data points are maroon squares with a light blue ring around them. Let's get rid of that halo around the squares and make them all red. All right, so there's our data set, plotted nicely, and it's ready to go into a PowerPoint presentation or into a Microsoft Word document. Okay. One thing that you'll notice about this data set is there does seem to be a strong trend between the height in inches and height in centimeters. And intuitively, this makes sense. If a student is tall by inches, they should be tall by centimeters as well. In fact, those things are related. There are 2.54 centimeters within every inch. So these should form a perfectly linear line, but there is obviously some errors in the way students make the measurements. So that's why we're seeing some scatter amongst the data. In order to determine how well they are correlated, one thing we might want to do is plot a trend line. And so one way to plot a trend line is to click the data set, right click to bring up the screen, and you'll see add trend line. You can see by default, it chooses a linear line, which is what we would expect for this data set. But you do have the option of selecting exponential, logarithmic, polynomial, powers, or a moving average. If you scroll down, you can also display an equation on the chart and an R-squared value. And so now that those things are up here, I'm going to drag them up and increase the font size so that we can see them better. And so what you see is this line that's drawn right here. Let's format the trend line to make it more obvious. Instead of making it light blue, let's make it a dark black, and we'll increase the weight a little bit so that it's easier to see. So in dashed lines right now, you can see our trend line nice. And so a question you may ask yourself is, what makes a trend line a good trend line? It should represent the data overall. And mathematically, there's a few ways that we can calculate that. I'd like to introduce a concept known as residuals. So residuals is the distance that an actual data point falls from the trend line. So in this case right here, you can see this point just above my green mouse. It sits directly on the trend line. So it would have a very small residual. It might even, in fact, be 0. This data point down here falls significantly above the trend line. So the distance from here, where my mouse is terminating, down to the trend line is large. By definition, that is the residual. We can choose another point, like this data point right here that sits just above, and you can see that that residual is considerably smaller, but it's not 0 because it does fall off of the line. This point down here falls below the line, so it has a negative residual. So what Microsoft Excel is doing when it fits a trend line to the data is it's trying to minimize the distance that the points fall from the line. So it's trying to minimize the sum of all of those residuals. And so what I'm going to do now is I'm going to move this table further off to the right, and I'm going to show you how to calculate your own residuals in your own formula. And you may ask, why is that useful if Excel already does it for me? Well, Excel does have some nice advantages, one of them being convenience. Unfortunately, Excel, its algorithms that it uses to determine the fits for the lines is not always perfect. Furthermore, if we go back to the trendline options, we have the option of exponential, linear, logarithmic, polynomial, power, and moving average. What you don't see is any of the many formulas that may pop up in biology, chemistry, physics, some of your advanced math classes. There will be points in your academic career and potentially your professional careers as well where you'll have to come up with your own formula and you'll have to fit data to it. And so we're going to start with a very simple example here. I'm going to show you how to fit data to a linear equation, and we can compare and contrast that to the Excel values. But it'll give you the same guidance and directions for fitting data to any type of formula you may have in the future. So what I want to know is, given x, my independent variable, what should y be, the dependent variable? And so we know that these are the actual data that we measured, and these have some error. So ideally, what should this value be given this input? So you can think of this as a function. If x goes into our function machine, what would it output? And so we know that equations fall for linears in the form of y equals mx plus b, where y is the y value, x is the x value, m is the slope, and b is the y-intercept. So this is the general equation for a linear line. So what I'm going to do is I'm going to create a box over here, and I'm going to call it m, which stands for slope. Actually, let me put it down here so it's more out of the way. M for slope. All right, well, that was unfortunate, but we'll continue. So m for slope, b for y-intercept. Those are the only two features that I can adjust within a line to come up with an equation that fits data. The x is always going to be an input, the y is always going to be an output. So the only way that I can control how steep or shallow this curve is by adjusting slope. And the other thing I can adjust is where it crosses the y-axis, which I do by adjusting b. Okay. So these are going to be my two values right here. So I'm going to write the equation. I want to find y, so I'm going to solve for y. So I'll put a y up here. We're going to say y is equal to the slope times the input, which is x, plus the y-intercept, which is b. And I'm just going to hit enter. It's not going to compute a value right now because I haven't put in values for slope and intercept. But let's say I say that the slope is about 2 and that the intercept should be roughly 0. So I'm just going to give it generic values to start with. So just based on those generic values, if I tell the input is 61 inches, it runs it through this function, it times it by 2, adds 0, it predicts that the height in centimeters should be 123. We'll continue this lesson in the 4th video.